Welcome to another video in this series on dimensionality reduction and factor models. Our previous video introduced the mini-series, and in this video, we're going to cover some introductory econometrics theory on measurement error and proxy variables, and specifically we'll discuss what proxy variables are, when they might be useful, and when they might actually make things worse. And the end story is that proxies offer a trade-off. They can help with omitted variable bias, but they might introduce problems of their own through mismeasurement. And I'll start off by introducing a comic strip from XKCD, which is one of my favorite web comics that discusses the principle of proxy variables and how they could be useful and may not be. So this is the comic strip. In the first frame, one scientist says, we want to study this variable, but it's hard to observe. And then he continues, so we're studying this proxy variable instead. And then the other scientist says, well, is it correlated with the other variable? And then the first scientist says, look, we don't have the funding to answer every little question. So the joke being that whether the proxy is actually correlated with the other variable is actually the most important part of this analysis. And then the other scientist is sloughing that off and saying, well, we don't have the funding to answer the primary question of our analysis. So that's just a little bit of humor. And let's get into the econometrics now. Let's start with the simple linear regression model from introductory econometrics. And if we suppose that this is a model that is going to be estimated on observational data, then we would be concerned that there's a correlation between x and epsilon. And this could be for a variety of reasons, but for now, let's just say that it's omitted variable bias. So there's something in epsilon that we either aren't including in our model or is not available in our data set that is correlated with both x and y. And this will cause omitted variable bias. So this will induce a non-zero covariance between x and epsilon, which, assuming both x and the omitted variable are correlated with y, would induce the bias. So one thing we can do to address this bias is to introduce another variable called a proxy variable. And this variable is ideally correlated with the confounder that we can't see or that we're choosing to exclude. And under certain conditions, this proxy variable can completely resolve our omitted variable bias. An example that is commonly given is we can't see someone's true underlying cognitive ability, but we can see some test score that measures that cognitive ability. Let's include that in our wage returns to schooling analysis, and that can maybe help with the endogeneity of schooling and ability being correlated, which would bias our estimates of the returns to schooling. So that sounds nice, but the problem is that proxies are imperfect and they don't exactly capture the confounder that we're after. And let's suppose that we have this proxy, which we call P, that is a proxy for the true confounder, which we'll call Z. And that proxy is going to have some measurement error attached to it. So P is going to be a function of Z, but then there's going to be some error around it. And if we assume two things about this error term on Z, if we assume that it's not correlated with Z and it's not correlated with our original X, then we'll have a situation called the classical errors in variables, which is CEV, or we just call this classical measurement error. And under these conditions, we can show that the OLS estimates that include this proxy are going to be attenuated towards zero, which is known as attenuation bias. And basically the intuition is that we have noise in the proxy that's going to dilute the true signal that Z would give. So because we can't include Z directly, we have to settle for this noisy proxy that will attenuate our estimates of both beta and the coefficient on P. So how does this work in a nonlinear model? Or if this CEV assumption fails so that there's some other type of error in the measurement? Well, in that case, then there's not really a tried and true rule on how the bias would go. We would call this non-classical measurement error, which basically just can be any type of measurement error that's not this ideal CEV measurement error. So the moral of the story from here is that if we introduce a noisy proxy, that's going to perhaps reduce our omitted variable bias, but it's also going to attenuate our estimate of the coefficient of interest. So what we need is a proxy that's so good that it removes the endogeneity of X. That's what these conditional expectations here are showing. It just says that If I know P, then I don't need to know X to learn what's in epsilon. And not surprisingly, proxies don't usually satisfy this requirement. This is a very tall bar to clear. But under certain conditions, we can use instrumental variables to solve this measurement error problem. And there's a long document written by Steve Pischke that I'll post in the companion repository to these videos that you could consult if you are interested in all sorts of results about measurement error in regression models. However, this instrumental variables approach is mainly useful in linear models. And as always, the validity of the instrument is something that we should question or at least critically analyze. And so basically, it seems like we have a trade-off between omitted variable bias and attenuation bias, because if we don't use the proxy, then we have omitted variable bias, but then if we use the noisy proxy, then we have attenuation bias. Another question might be, what if we have many correlated proxies? And this could come up in a number of domains, but just for the example that I gave earlier, we might want to triangulate somebody's unobservability by having them take multiple tests to see how they score. So this would give us multiple different proxies that we could use. But then the question is, how do we know which ones to use as proxies, especially given that each test would have some measurement error in it and that the tests are highly correlated with each other? So this is the problem that we will discuss in the upcoming videos. And it definitely is not clear from the classical measurement error approach how we would be able to use all of these different proxies together. Before we tackle the multiple proxies approach, I wanted to introduce a fundamental dimensionality reduction technique that's related to factor analysis called principal components analysis. And this is one way to reduce the number of proxies, if we have multiple proxies, into a single proxy that could be used in place of all of the other ones. So we'll talk about the advantages and disadvantages of that approach, and I hope to see you in the next video.